I've given you sort of the formal argument for what's going on, but let me just sort of summarize and give you my pictorial way of thinking what's going on. So this, especially if you had trouble with the derivation, this is really the upshot of what's going on. I forgot to put the B in here. Okay, so don't look down there. Okay, so what we've just sort of seen in the case of geometry, is that classical fields, the way they enter into the action is the same as coherent states of quantum fields, in particular the graviton field. And so you should not be that when you see a classical background geometry in string theory, you should not think, there's some given space-time in which it's living. What you should think is, there's some background field of strings, which of course are just interacting according to string theory with the string. Because if you're interacting with a coherent state of a quantum field, those quanta should in fact be thought of as strings in the appropriate modes. So I have a sort of general picture of this, and the first time here's some nice curved space-time, but if you zoom in on the curved space-time, you see that it's really a coherent state of a quantum field of gravitons, and that's supposed to be my picture of a coherent state of gravitons. But if you then look even further, each one of those gravitons is really a string. Okay, so go the other way. A string corresponds to a quantum of the graviton field, and when you have enough of those quanta put together as a coherent state, it appears as a classical field, and that's the string picture. So, but now my kind of some important comments on this, which I guess I will just make and then we'll pass over. I've really just said it already. We just worked that out for the metric field because we were interested in a classical curved background for the string and its nature. But the same reasoning will apply to any classical matter field that you might want to couple to the string, if it corresponds to a string, a mode of the string, if its quanta correspond to modes of the string. So, for instance, if you wanted to have a classical scalar field, we saw that there was a scalar field in the string particle. One could add a term like this. R is a kind of Ricci scalar for the curvature of the string world sheet. This is actually the term that you add to the Polyakov action if you want to have a background scalar field. The very same reasoning in terms of, that's going to add an exponentiated factor to the path integral, to the path amplitude of any path. But you'll again see that it just corresponds to operator insertions if you have a coherent state of the scalar quanta, which themselves are to be thought of again as states of the string. So, at the string mode level, particles of matter and gravitons are nothing but different states of the string, and so interchangeable. They're just different internal states of the string. They just correspond to different vibrations of the string. If you took enough stringy quanta to build a quantum field, I'm not saying this is dynamically possible, but in terms of the states of the string, you could take take a collection of strings, excite them all into graviton states, and they would form a coherent state of a quantum field state of gravitons, of the graviton field. Change the excitations of all of the strings into scalar excitations, and the very same strings form a state of, at this level, form a state of the quantum scalar field, or whatever other field you want in string theory. The quantum fields are fully unified because you just change the state of the string to change what quanta they're composed of, as it were. And, of course, then that carries over into the classical case as well. Curved geometry, if you want to, again, I'm not saying that it's dynamically possible, but you can take your collection of strings, turn them into a state that corresponds to a classical curved geometry, take the same set of strings, excite them differently, put them together, and get a magnetic field or a scalar field out of them. These are all just different collective states of strings. Okay? And so matter and geometry are unified at this level about their nature. Okay, remember that was one of the questions that we sort of started with. However, something important has not been said yet. So, and this point I haven't said explicitly but want to emphasize, we've really been talking mostly about systems where I just have one string. And I can kind of excite whatever modes of the string you like as much as you like. That doesn't, in a quantum field, in 3+ regular quantum field in space-time, every time you excite a mode, you're creating a new particle with that momentum. That's not what happens with the string. Of course, when you excite the modes, what you get is different values for the mass operator m squared. You're getting different particles. You're not getting more particles. You're changing what particle the string appears to be. Okay. So if I want many particles, many stringy particles, I can't get it from a single string. I need to have many strings. Each string kind of corresponds to one particle in some particular type or superposition of types. So, of course, I'm assuming here that I actually have multiple strings. Moreover, a coherent state, if you look at it, doesn't have a definite number of quanta of excitations in it. It's actually a superposition of one excitation plus two excitations plus three excitations. It has an indefinite number of quanta in it. So not only do I need many strings, I need to be able to have indefinite numbers of strings. And I need to be able to annihilate and create and annihilate strings. That needs to be what string theory allows you to do. And so I can create one string, and I can create two strings and have a superposition of those. That's got to be part of the story. So for this story to be fully justified, one needs a string theory in which strings can be annihilated and created, not just a sort of single theory, a single string theory. The difference is just that between quantum particle mechanics and quantum field theory, between quantum particles and quanta properly, things that can be created and annihilated. So what's needed to fully fill out this picture would be a theory in which the strings weren't like particles, but they were like quanta. And there is a string field theory, but as far as I know, it only works for bosonic strings. It's a bosonic theory. And nobody actually knows what has a string theory that does this has creation and annihilation of strings in full generality. That's really what M theory would be. So, as I said, at one time, the natural thing to look for was just a kind of second quantized field theory of strings that had strings annihilated and created. I think today people don't think that that's going to be the exact form of the theory, but that's going to be whatever the theory is, that'll be a reasonable approximation to what happens in that theory. Okay, so this is very much the same point I made earlier. You can put in by hand that strings can be created and annihilated, can split and join, in other words, but there's no full theory that tells you how that's supposed to happen. It's really the same point. And finally, okay, I've probably been saying things that are a little stronger than I would to be fully careful. Of course, when we did our analysis, we didn't find that all of G mu was constituted of gravitons. We expanded it in terms of a Minkowski background plus a field that lives in it, and this is the graviton part. If you go back and look at what happened, the story we told still is living in some sense in a Minkowski background. Okay. So what's the significance of that point? Various things have been sort of said about that. One thing you might say is, look, I'm just going to really take a worldsheet point of view at this point, and I've got the fundamental degrees of freedom of the theory of this x mu nu field, and I'm just not going to be able to do anything unless I know how that's a vector, unless I have an inner product for that vector, and I've got to write something down. The Minkowski metric is sort of really just the easiest way of taking products of vectors that I can come up with. So that's sort of I don't know how to go back on here. No. No, it stopped. Okay. Don't know what I'm doing now. Okay. Good. Okay. Luboš Mortal has made another point, which is, I do split this G field into, it's supposed to be an eta or Minkowski part plus another part, but the analysis could be done on other divisions into a background metric, sort of a classical part and a stringy graviton part. And so there's no physical meaning particularly to the choice of the Minkowski background. I have to perform the split to do the physics at all, but there's nothing that things would go through the same and the physics would be the same if I'd done the split differently, and so there's no kind of this is not an invariant of the theory. There's no physical significance to the Minkowski metric, just the presence of some classical background. I think there's some sort of technical points about that I don't fully. Writing things a tensor as a sum of two tensors, right? That's just trivial. But whether the story really goes through exactly the same if you do that, there's some things I don't fully understand there. Okay, so I wanted to acknowledge that there's still a classical kind of part here, even if the sort of curvature part has been analyzed in stringy terms. And just to refer back to yesterday, of course, I've just done all of this story in one of the dual. I mean, if this story is being told in a topologically closed dimension, then there's going to be a dual to this as well. And so, although there's a Minkowski metric, for the reasons we looked at yesterday, you might want to say that the actual size of this space-time in which it's happening is indeterminate, is unphysical, is not an invariant. Okay. Even though this Minkowski metric is there, sort of its inverse has got to be another sort of physically equivalent because of the T-duality. Oh, I see why it does. Okay, ignore the equation for a second. Okay, so those were some thoughts, just some thinking through. And that picture really is a summary of the payoff of what we said in the first lecture today, and then some observations about what we have shown. As I said, to really see that we have gravitons, we would like to get the Einstein field equations out of this as well. What we've sort of seen is that those, I keep calling them gravitons. I mean those massless spin-2 string states. What we've seen is they appear, they play a role as classical background curvature. So they certainly have the geometrical significance. To be quanta of the gravitational field, it better also be the case that those classical states that correspond to the coherent states of those quanta obey the Einstein field equations. And I want to the last thing to do is to explain why that is so. And the argument here depends on some considerations to do with symmetries. Okay, what is a symmetry? In this context, we'll take the symmetry to be a transformation that leads, so just classically, a transformation that leaves the action unchanged. If it leaves the action unchanged, it's going to leave unchanged which trajectory minimizes the action, and so it's going to leave the physically possible allowed trajectories unchanged. It's going to leave what the solutions of the theory are going to be unchanged by this transformation. That's what a symmetry is. Then there's lots of beautiful mathematics related to that, including Noether's theorem that tells us that there are going to be conserved quantities, and that's a very important feature of 20th century physics. Okay. So suppose I have a classical symmetry of the action. Now think about what happens at the quantum level. So you kind of might think the path integral tells you, Feynman tells you to sum up a whole load of exponentiated actions, one for each path, and if there's a classical symmetry, it leaves S unchanged, so it has to leave this exponential unchanged, and so any classical symmetry on first sight must be also a quantum symmetry. It's going to leave the value of the path integral unchanged. But that's not right, because this is a path integral and not really a sum over paths. And since there's an integral, there's also a measure in this quantity. There's the measure of the integral, and that's where you can sort of see that here. The paths aren't discrete generally, but continuous. So, I know I keep doing it. Okay, sorry. Okay. So actually, if you thought about trying to do a sum over paths which are discrete, you'd sort of pick a sampling of paths at regular intervals. You'd calculate the action for that one path, and to kind of compensate for the fact that there were actually a lot of paths around it, you'd sort of multiply by a small area of the space of paths. That would, instead of adding up for that continuous number of paths in that space, you'd figure out the action for one of them, assume that the action was close enough for the ones around it, and multiply by some number that told you the density of paths in that space. Your path integral, your path sum would have to look something like this. There'd be a term for the number of paths around each of the sampled paths. And then, of course, if I transform that into an actual integral, what you have to take is something that is an integral over the space of paths, and for each one, the exponentiated action. If you know about path integrals, I'm just saying it's a path integral. The point here was just for people who haven't thought about functional integration and functional differentiation. Because there's a continuous number of paths, really what you have to do is something that's an integral, and so depends on the density of paths around each point. And now we can see if we have a classical symmetry, e to the I, that means S is invariant under the transformation, so this term is invariant, but this term may not be. A change of variables may well change the measure. And in particular, we do have the case where some classical symmetry changes the measure and so changes the path integral. Something that can be a symmetry at the classical level, but then is not at the quantum level. Such a thing is called an anomaly. Sometimes anomalies are good. In fact, they allow pion decay, which is observed, for instance. But at least according to quantum field theory law, the sort of received understanding of quantum field theory, you cannot have an anomaly in a local gauge field theory. So a theory where there's some internal degree of freedom that can be varied you have a symmetry when you vary it differently at every point of space-time. So local gauge theory, if that's the symmetry of the classical theory, but not for this reason of the quantum field theory, that kind of anomaly leads to a pathology. It leads to, in particular, generally to probability not being conserved. The theory won't be unitary. And that's not, you'll go from probability 1 to probability 1/2 or probability 1.5 for things happening, and that doesn't make any physical sense. Okay, and in fact, that's a crucial component in the standard model, that you can't have anomalies in these local gauge theories, puts constraints on what can actually go into the standard model that are non-trivial. This is a hugely sort of important topic in idea in high-energy physics and quantum field theory that philosophers have said next to nothing about. It's also the crucial idea in string theory. So, talking about that very quickly, what are the classical symmetries of the string? So I'm thinking about the Polyakov action. You need to write it down, or that was the Nambu-Goto action. Let's just talk in those terms. I wrote the metric, we wrote the metric, if you write the metric explicitly, then it has to have space-time diffeomorphism invariance, just under arbitrary changes of coordinates. Not surprisingly, it also has the symmetry under arbitrary changes in the worldsheet coordinates. Not surprisingly, we picked a Minkowski background. We'll talk about Minkowski, sorry. We're going to pick a Lorentzian metric, so it has local Lorentz invariance, not surprisingly, or general Lorentz invariance for flat space-time. Most importantly, what's called worldsheet Weyl transformations, which are, in some sense, one of the most important features of the formalism of string theory. To really see that, you need to look at the full Polyakov action and not the form. I've broken this Weyl symmetry in the way that I've written it down for you. So you have to go look at the textbooks to see exactly what this means formally. But I can tell you intuitively what the Weyl symmetry means, right? The Nambu-Goto action just says that the action is equal to the worldsheet area. Okay, so imagine your sort of worldsheet. I'll visualize it for you here. Okay. All the physics depends on is the area of that. But imagine you thought, and your coordinates sort of make this happen. The string's made of different points. The action's not going to be changed if somehow I move. So suppose I think this point is the same one as this one, and there's sort of a trajectory sort of from one to the other. Well, suppose I move things around, so now that was like this one was identified with this one, but without changing the area. So imagine my worldsheet is sort of elastic, and I'm shuffling things around without changing the area or indeed the shape of the thing. Okay? That's nothing physical to what I've just done there. So in fact, it can't really be a physical difference at all that I've been making there. In short, any particle, any point of the string at any other really could be, any point of the string at one time could be re-identified with a point at any other time, and so I'm free to, if I think this point is the same at this one, that's space-like, that's time-like to it, I'm free to move the later one anywhere I like without changing the physics. There's no fact about how it's related to this one other than being time-like. Because I'm just going to move it along the worldsheet without changing the shape of the worldsheet, so without changing the space-time area. I mean, another way to see what's going on is, and this is where I would bring my spring out. Okay, if you have imagine you have a classical spring, and this is its sort of natural length, and I pull it to here. Okay, if I just pull the ends, you know what state it's going to be in. It's just going to be equally stretched all the way along because that's the lowest energy state of that string, of that spring. But I could sort of anchor at the ends at either, anchor the two ends and sort of pull it more here, and so it's more stretched on the left and less stretched on the right. You know what's going to happen if I let go? It's going to ping back until the tension is even along it. I'm going to pull it so there's more tension on the left and less on the right. That's not an equilibrium state. I have to hold it there. Okay? But there's nothing like that in the string, because all it cares about is the area. There's no such thing as sort of stretching it one way rather than the other so that it pings back. And of course that's because it's not a Hooke's law string. It's not like a Hooke's law object where the tension depends on the extension. The tension is just constant. Okay. So I have this symmetry where you can just think about, if you just identify the points and move them around however you like, so that they're ones that were close together are now farther apart in some sense. As long as the total world sheet stays the same, that's a complete symmetry of the theory. Doesn't care at all about how the parts of the string are related, the string world sheet are related to one another, just what the whole thing looks like. That's really the Weyl symmetry. Okay? All that I really have to preserve is the light cone structure on the string. Okay. There are two very important consequences. So that's the classical level. There's Weyl symmetry. It is, in fact, a local gauge symmetry. So it has to be preserved at the quantum level. Otherwise, I don't have a consistent theory. I don't have unitarity. But it's provable. Quantum Weyl symmetry requires 26 dimensions for a theory with no fermions, 10 dimensions for a theory with fermions. Moreover, it requires, and this was approved by Friedan in the first place, and then an important paper by Friedan, Calan, and some other people. Again, to avoid the quantum anomaly, which is not just a matter of choice, you just don't have a consistent theory if the anomaly is present. This is the important result. At lowest order, so this is a perturbative calculation, and lowest order means, as I said earlier, in that alpha prime. So lowest order in something that's telling you that's looking at how curved space is. Background fields satisfy their Einstein field equation. So if there's no other background fields in the action, I just put in some an h mu nu to give some curvature, then the g mu nu is going to have to satisfy the vacuum field equations, which say that they're Ricci flat. The Ricci tensor is 0. It doesn't mean space is flat because I can have waves. If I put in that scalar term background field, okay, again we're thinking of that as a coherent state of stringy scalar quanta. Then I get then there's stress energy associated with that field. But again, the result then changes for Weyl symmetry that to lowest order in the alpha prime expansion, the appropriate Einstein field equations appear. Okay. If you look at the second order term, whatever I can't remember if it's alpha squared or alpha prime squared, but whatever the next order term that appears, you'll get different contributions, which then sort of classically look like quantum corrections to the Einstein field equations. But to lowest order, so in alpha, you get the Einstein field equations. So that is, I would say, just what you would like. Of course, what that's then saying, so I'm now imagining a string, say in the latter case, where I have both curved space-time and a scalar field, and what we've just seen, what this result means is they have to be related. When you look at the classical description, according to the Einstein field equation, but ultimately both of those, of course, now you have to think of this picture twice over. There's curvature and there's a scalar field. Both of them are composed of quanta, which ultimately are strings. Saying that these two classical fields are related in a certain way, according to the Einstein field equation, is ultimately to say that the strings that make them up are related in the appropriate way. People often think of this result as merely a consistency result on what kind of classical spacetimes strings can live in. But that ignores what we talked about in the first lecture. those classical fields really in the full string theory picture are thought of as complicated multi-string states. So it's not just a consistency on a given classical background. What the Einstein field equations are, by this result, are consistency constraints on what multi-string states are possible. Okay. It has an understanding that's fully stringy. And then, of course, because we have the Einstein field equations, well, string theory should be applicable to cosmology, and indeed there are people who have created models of black holes at the Big Bang. It's from another talk I have, which sort of shows a stringy model of a black hole and allows you to kind of model string processes in black holes. The way people actually do it involves going to supersymmetry and having fermions, and the situation is more complicated than we have looked at. But this result about the Einstein field equations still goes through in that case. So because of this, right, string theory really, in principle, and there sort of is and was an industry of showing that in practice can model cosmological situations according to this picture. Okay, well, I see people waiting out there. I will put up the last slide, but I won't talk through it. You can see it. That's for the sort of review of everything we did. So maybe I have time for one or two quick questions if people aren't here. But otherwise, thank you very much, and thank you very much for your patience. If we don't have time now, I'm happy to talk to people outside. Thank you.